Hello, welcome to GUM Uncertainty Framework Part 2. I'm Richard Leach, Professor of Metrology and leader of the course. So let's just review what you did in the first part of this uncertainty course. So we looked at systematic and random errors, we looked at the various statistics, distributions that you need. We didn't cover confidence intervals in much detail, and we will talk about those a little bit today. We looked at the standard uncertainty concept, propagation of uncertainties, and then we looked at the three methods for applying that propagation process. And today we're going to look at examples where we have more than one variable, which is often the case. And then we'll look at how to express the final result and how to round the figures, etc. Okay, I'm just going to pause for a second just to make sure this is recording. Yeah, it is. Okay. Right, so multiple variable measurement. So by that we would mean, and the example I'm going to give you is that we might be measuring density, and to do that we have to measure the mass and displacement, or mass and volume. And so that's what we class as a multivariable measurement. So how do we deal with that? So first of all, we have to propagate the systematic effects. So we have the various effects. Our model equation basically is y is some function on the various variables. So let's do an example. The density of the ball, which we talked about in the last lecture, that depends on the mass and the volume, and of course the volume is related to the diameter. So our model equation, rho equals mass over volume equals 6 times the mass over pi d cubed. Hopefully you can all see where we get that. And notice I put the two pictures I've put in here are the mass measurement and the displacement measurement, and it's important to realize that they're separate measurements. So you can't measure the mass and the diameter at the same time. When you could try, but it would be difficult, and you wouldn't typically do that. So just bear that in mind when we come to talk about correlation. So we're going to try and propagate the various systematic deviations that we get through our model equation, which you can see there, and for the example of the ball density. Now we have that from the previous lecture. We know that we can express, one way of expressing the differential in y is to sum over the partial derivatives of the various terms, the x terms, and then multiply those by the differential in x. That's just from simple calculus. So let's do that. Let's find all those partial derivatives for the various variables in our model equation. So we can say delta rho equals d rho by dm times delta m plus d rho by dd times delta d. So that's the two variables, the mass and the diameter. So solving for the partial derivatives, go 6 over pi d cubed delta m minus, notice it's a minus there because we've got the d cubed in the quotient, so it becomes a minus 18m over pi d squared. So we've dropped a power off the d because of the partial derivative at times delta d. And that's equal to, if we just put solving back to the original equation, equals rho over m delta m minus 3 rho over d delta d. That's from our relationship we found earlier. Okay, so if we want to look at so we can change the formula from the other side to make it a relative error. So delta rho over rho equals delta m over m minus 3 delta d over d. So if we wanted to find the maximum systematic effect, and I've put first order in brackets, don't worry too much about that now, we'll talk about the correlation later. So the maximum deviation is calculated by finding the absolute value, or the absolute value of the addition of those errors. So that's really as large as the deviation could be. And it's highly unlikely to be that. So often you would only use this to estimate what the range of the uncertainties might be, but you would use more the statistical calculations that we'll come across, that we'll cover in a minute. Typically, so just adding up those terms will give us the worst case measurement, and that will give us the absolute value of delta m over m plus 3 times the absolute value of delta d over d. So that minus sign disappears. But so let's consider now the propagation of the standard uncertainty. So we're not just talking about the error terms now, we're talking about the standard uncertainties, or in this case, the standard deviation. So the standard deviation will always be positive. So you won't come across a negative value there. You can't have a negative standard deviation because of the square root sign. So in this case, the delta rho squared, the standard deviation, is d rho by dm delta m, d rho by dd delta d squared. So squaring that term, we get the squared terms in each of the terms, and then we get also this correlation term, as it's called, which is 2 d rho by dm, d rho by dd, delta m delta d. So the last term is what we call the correlation term, and we're going to assume that's 0. In many cases it is, or it's either 0 or it's very, very small. Subtly, in this example, it must be 0, and I'll come on to tell you about that a bit later. So look at converting that into standard deviations. The standard deviation in rho equals rho over m times the standard deviation in m squared plus 3 rho over d times the standard deviation in d squared. So in general, if we've got a function which is y equals f of x1, x2, where x1 and x2 are the multiple variables, then we know that delta y equals the sum of the partial derivatives times the error terms, and the equation for delta y squared is the squared terms added together plus this second term, which takes into account the correlation. So that's the sum of all the cross terms. So in terms of statistics, just looking at that cross term there, in terms of statistics, we know that the standard deviation equals the equation on the left there, and this thing I'm defining here, which is delta sigma xi, delta sigma xj over xij, the standard deviations in those terms, that's what's called a correlation coefficient. So you don't need to go into too much details. You can look those up, how to calculate those, which gives us and actually I notice I've missed out the summation term, so there should be a summation over x and y in the correlation coefficient there. Oh, sorry, no, the sum is in there, yeah. So which gives the equation sy squared equals the first order term in the partial derivative squared plus the cross term as well, and you notice that you've used that correlation coefficient there. So in general, that's the general equation that we get, that you have your sum of squares plus that term in the correlation, which involves that correlation coefficient. If we can assume that the properties are uncorrelated, and remember that we said because we were measuring mass and diameter separately as separate measurements, then those terms must be uncorrelated, that one doesn't affect the other one. So we can say that r equals 0 in our particular case. In that case, the standard deviations squared are just the sum of squares. So standard deviation in a measurement result is the squared sum of the standard deviation of all the separate parameters of this result. And in terms of uncertainties, so if we say that where our uncertainties are modelled by the standard deviation, remember it could be the standard error of the mean, then again, the uncertainty squared is just the sum of the partial derivative squared times the uncertainty term squared. So the standard uncertainty in a measurement result is the squared sum of the standard uncertainties of all the separate parameters for this result. So we used quite a complicated approach there to find what sort of everyone knows from their basic A-level physics or basic A-level engineering, because you're always told to add the sum of squares to when you're calculating your errors for your lab reports and things like that. But this is where that comes from. So it's an approximation, and it's an approximation because we throw away that correlation term. So back to the ball density example, the uncertainty in rho must be calculated from the uncertainty in mass and the uncertainty in diameter. So once again, in the middle there's our model equation. And the measurements, if we're calling these from last week or from the last lecture, sorry, is 24.735 millimeters. The uncertainty in the diameter, which was repeat measurements, was 5 repeat measurements if I remember rightly, and that gave us a standard deviation of 0.03 millimeters. The mass was 19.8 grams, and we're saying that the resolution of the mass scale we're using, and you can see that from the digital reading in the picture, is about 0.1 grams. So modelling that as a rectangular distribution, we say that the uncertainty is 0.05. Notice 0.05 because it's 0.1, so we need to divide that by 2√3, equals 0.03 grams. So that's the uncertainty in the mass measurement. So going back to our propagation of uncertainties, so there's that sum of squares equation. Again, and we just recalled from the previous slides, and thus we can just take the square root of that to give us the uncertainty, and plugging in the numbers, blah blah blah, that gives the sum of 0.038 squared plus 0.009 squared rooted, which is 0.01 grams per centimeter cubed. So that's our uncertainty for multiple variables. In this case it was mass and diameter, and but now we get the uncertainty in the density measurement without considering the correlation terms, remember. But we'll come back to those. So the standard uncertainty U of rho is 0.01 grams per centimeter cubed, and just out of interest, well, I'll show you how to do this a bit later, but the uncertainty represents 95% probability, and we get that by multiplying by a factor k equals 2. Again, don't worry where that's come from. So we would quote that as the value for the density is 2.49 plus or minus 0.02 grams per centimeter squared. So here's I want to present to you now the spreadsheet method. So this is how we would combine the uncertainties, and it's a nice way, this, of setting up an uncertainty budget so you can take into account all the various terms in the budget and then add them up to the final result at the end. So this is a typical table that you would produce. So for every uncertainty budget I've ever done, I always produce a table like this one, and you can set these up in Excel easily, or you can set them up in MATLAB, and then you just plug your numbers in and it will calculate the sum of squares for you, or correlation terms if you need them. So let's go through the various parts of this table. So if we look at the columns, the first column is the symbol, so that could be mass and diameter. Then there's the source of uncertainty, so a small description of the uncertainty. The value, this is the estimate of the uncertainty from what you have, so that could be a standard deviation, could be a limit, etc. Notice that you would always put in here it's essential that you put in the units, because if you've got different units, for example, you've got mass and diameter. Mass is in kilograms, of course, and diameter is in meters. You can't add those up. You're going to have to convert somehow them to the same units before you can add those up to give you a final uncertainty. And it's that partial derivative term which allows you to do that. That will convert them all to the same units. Probability distribution, so we went over those. Could be rectangular, could be normal, and there are others, rectangular, triangular, etc. Then there's the divisor, and this is the factor which normalizes the value to a standard uncertainty. So for example, this will go back to the K factor that you saw on the previous third slide, and it depends on the confidence level that you've got. So we'll cover that later in the lecture, but you need to always convert to standard uncertainties, and there will be a particular divisor for that, but that will become clear near the end. And then there's the sensitivity coefficient. So this is the coefficient which converts you to the consistence unit. So that's your dy by dxi term. So that's how you convert to so that all of the terms are in the units, and you can safely apply your addition or your quadrature addition to allow you to give a final result. So and then there's the standard uncertainty value which you get, which will be the value from column 2 divided by the divisor and all of that multiplied by the sensitivity coefficient. Then we have a last term, which is the effective number of degrees of freedom. So I'm just going to say, just ignore that. That's a term which gives you uncertainty in the uncertainty. Sometimes it's ignored. Sometimes people put that it's infinite, which is effectively ignoring it. But we'll cover that later. Just ignore that column for now. And then the rows going crossways, there's one row for each uncertainty type. So in our case, that would be mass and diameter. There's one row for the combined standard uncertainty by summing in quadrature. So that would be that the sum of the partial derivatives in our case times the uncertainty squared, the individual uncertainties squared. And then the final row shows what's called the expanded uncertainty. So that's that K factor, which mysterious K factor, which I haven't talked about yet. I will talk about at the end, which gives us a particular confidence level for the uncertainty. So the expanded uncertainty is what finally is reported. So here's the spreadsheet model. I've filled it in for our density example. So the symbol M, M in this case, and if we just look at the mass term, so the mass is, the measured mass was 19.8 grams. The value of the uncertainty was the error was 0.1 grams. We said that was rectangular because it was a resolution term. So our divisor was 2√3 to normalize it to 1 standard deviation. And then our sensitivity coefficient, so the partial derivative, was rho over m in this case. And then we divide by the divisor, multiply by the rho over m, and that gives us the standard uncertainty, which was 0.028. Don't worry about degrees of freedom for now. Diameter, the value which we got as a standard deviation was 0.03. We assume that's normally distributed, so the divisor is just 1, and the sensitivity coefficient was 3 rho over d, and that gave us that standard uncertainty of that value. Then finally in rho we get by the sum of squares of those two values, and that gives us 0.01. Okay, we can also apply the Monte Carlo method to this approach. And again, I've summarized the values that we would use for the measurands and the uncertainties, and the model equation at the top there. So let's look at how we would set up a MATLAB code. It's very easy. So we can model the diameter and rand n gives us a rectangular distribution. The mass is a normal distribution, and then the rho we just use our model equation to give us that, and then we repeat that many thousands or even millions of times. So that gives us a row value, standard deviation, and you see we get from this, when we run this, 0.0098, which is pretty damn close to 0.1 that we found with the spreadsheet model or the sum of squares model. And also in MATLAB, you can calculate various confidence intervals and things like that, but don't worry about too much about those now. So the result from Monte Carlo gives us 0.019. The result from the standard model gives us 0.02. So it's pretty damn close. So the final statement. We've done all of this mathematics, etc. We found our uncertainty terms, and we found that final standard uncertainty, what's called a combined uncertainty, because we've added up the various terms. How do we finally state that? I've hinted at it a couple of times. First of all, we need to look at degrees of freedom. You need to be able to you need the degrees of freedom to be able to calculate that K factor. So degrees of freedom, what's usually called nu I, are determined for each uncertainty term. And there's a few ways to get them. So for type A, in other words, if you've done several repeat measurements, then the nu I would be equal to the number of measurements minus 1, where ni is the number of repeats that you do. And that's I don't want to go into the details of exactly what degrees of freedom are. You can look them up. Again, they model the uncertainty in the uncertainty. So how uncertain are you about your uncertainty value? And it has a certain number of degrees of freedom. It's a statistical term. You can look it up if you like. We don't need to worry too much to be able to do an uncertainty budget about what it is. For type B, it's normally they're estimated according to a relative uncertainty, so the uncertainty divided by the actual value, and that gives us judgment of the reliability or the confidence, and typically you use this equation, so it'd be half delta U over U to the minus 2. Then notice as delta U goes to 0, then the degrees of freedom go to infinite. In other words, and in many cases, when we're talking about type B uncertainty estimations, we would typically model them with an infinite number of degrees of freedom. So there's also an equation known as the Welch-Satterthwaite equation, which allows you to then, once you've got the degrees of freedom for the various terms, you can calculate them for the effective number of degrees of freedom for the final result. And that's calculated by finding the fourth power of the combined uncertainty divided by each uncertainty divided by its degree of freedom, again to the power of 4. And degrees of freedom are always rounded up to the next integer for this equation. So you just plug the numbers in, and it gives you an effective number of degrees of freedom. So if we go back to our spreadsheet model for the density measurement result example, and now I've filled in the degrees of freedom. So I've assumed, because it's rectangular, and therefore I pretty much know everything about, I know it's somewhere within that rectangular distribution without any doubt whatsoever. It cannot be outside that, because I know the resolution of the system. So because of that, I can model it as an infinite number of degrees of freedom. Then for the diameter measurement, I took 5 measurements, n minus 1 gives 4 degrees of freedom. Then if I plug those two values into the Welch-Satterthwaite equation, it gives me 66 degrees of freedom. In many cases, a number like 66 can be statistically treated like infinity. So it doesn't seem like infinity, but as far as the tables are concerned that we're going to use this for in a minute, it is. So the expanded uncertainty is found, and this is the thing that we would typically quote. The expanded uncertainty is found with the following. It's the combined uncertainty multiplied by some K factor, which models the confidence So the coverage factor, as it's called, gives the level of confidence in the result. And you look it up in basic t-tables. Remember, we talked about the t-distribution in the last lecture, so which models the normal distribution. So we can use those t-tables with the number of degrees of freedom to find that k value. So here's standard tables. You can find these. You want Google search, you'll find them in seconds. You notice your columns in here. You've got the degrees of freedom, and then the confidence level that you're looking for. So it might be 90, 95 is typical. That's why I've put those in bold there. So let's just have a look at some of those. So notice if you had in 66 in our case, your confidence level or your K factor, the expansion factor is 2. And notice also 1.96 at infinity there. Most people, and in most uncertainty budgets, by far the majority of them, people say if it's 1.96, it's infinite, then it's 2. So that's why I said that 60 is pretty much the same as infinite. But it's not. It's worth pointing out that people often just say, right, I've got my combined uncertainty, I'm going to multiply it by 2 to give me a 95% confidence. But that's not right, because if we've only got 9 degrees of freedom, it should be 2.26, which is going to give us a larger value, i.e. it's showing that we haven't got so much confidence because of a lack of degrees of freedom in the measurement. But these tables, you can use your Wells Satters weight, calculate your degrees of freedom, then look up your value at 95% if that's what you're asked to quote, and it will give you that K factor, which you multiply by your combined uncertainty. So there, that's just summarising that for if we want it at K equals 1, approximately, of course, this is for infinite degrees of freedom. It's about 68%, K equals 2, 95%, K equals 3, 99.7, etc. So, of course, those are approximations. So how to express the final result? We're there. Well, to write down the measurement result and the uncertainty, and we can't just express the uncertainty. We need the uncertainty, the coverage factor, and the level of confidence. So here's how we will quote it for the ball. The ball density was 2.49 grams per centimetre cubed with an expanded uncertainty of plus or minus 0.02 grams per centimetre cubed at a coverage factor of K equals 2, giving us a level of confidence of approximately 95%. Notice approximately 95% because of we can never have it exactly. Okay, so that's it. That's what we do. So this is an important thing now. So how do we round the uncertainty at the end? And there's various rules for doing this. They come from the NIST website, in fact. So there's 3 ways of rounding, and you can use either as long as you're consistent and you choose one of these for your lab or for your particular manufacturing concern. Identify the first 2 significant digits in the expanded uncertainty, round the expanded uncertainty following options A, B, C, which I'll talk about, and round the reported measurement result to the same number of decimal places as the least significant digit in the uncertainty. So if you know what that is. So option A, which is called the even odd method, if the digit next beyond the one to be retained is less than 5, keep the figure unchanged. When the digit next beyond the one to be retained is greater, then increase the figure by 1. When the digit next to it beyond the one to be retained equals 5, the digit is even, leave it unchanged. If it's odd, increase by 1. So that's just a rule that you can apply. When there's 2 plus figures are to the right of the last figure, consider them as a group in rounding decisions. The standard spreadsheet rounding is to use standard rounding practices that are used in the spreadsheet, basically. So you accept that you're going to use whatever Excel uses. And the last one is to round uncertainties to the next largest value when there are any digits beyond the second significant digit. Okay, just going to say a few words about that correlation term, and then we're done. So let's remind ourselves in general, if we've got our model equation is y equals a function of various variables, then the error in y is that summation term. The error squared is the summation term plus the correlation term, which includes that correlation coefficient. So what do we mean by correlation? So if two input quantities are correlated to some degree, this means that they are mutually dependent. In other words, if we think of the mass example, if it turned out that measuring the mass affected the diameter measurement in some way, then I would have correlated terms. This is clearly not the case in our example. But if you imagine you were, for example, measuring a surface, then and your probe that you're measuring, it has a finite diameter size. So you're running a stylus across a surface to measure it. Then your probe has a finite size. Because it does, then the way you measure the one point would be affected by the slope angle on the surface and the diameter of the sphere for the next point. So the points are, it acts like a filter. The probe acts like a filter. If you've got a filter with a filter kernel, then that filter will mean that your points are always correlated. So in surface texture, the points are always correlated. Although many people, when they're calculating uncertainties for surface texture, if they do, then they assume uncorrelation, but it's not strictly true. And if you've got an optical measurement, then the size of the influence of the beam will affect more than one point. It'll affect the point plus its neighbouring point, so it's correlated. If you've got positive correlation and you ignore it, you will tend to underestimate your uncertainty, and if it's negative, you'll overestimate your uncertainty. But when can we ignore it? The answer is when, well, this is one answer. So when the covariance uncertainty, so that second cross term, is significantly less than the single component terms, so the first order terms. So let's work that out for our example. So that's what we mean when the partial derivatives times the uncertainties squared is a lot bigger than that cross term. So let's go back to our example, plug some numbers in, even though it's a silly example because they're not correlated, but pretend they were. Then if we look at our model equation, including the cross terms there, the correlation terms, the uncorrelated value of u squared is 0.0001. That's squared, remember, we take the square root to give you the uncertainty, but that's the uncertainty squared, 0.001, and then that cross term, plugging in all the values, is 0.00007, which is maybe not insignificantly smaller than the 0.0001 value there. So we would need to consider that. I think if we didn't know from the physics of the situation that this was uncorrelated, then I would consider adding that correlation term in. So we said that the answer was when the covariance uncertainty is significantly less than the single value, but also when it is blindingly obvious that the measurements are not correlated, then we don't need to consider it. So in the density measurement, the mass has no effect on the that should say diameter there, not density measurement. Okay, so we're coming to the end of our path towards uncertainty. So let's just go through those various steps again that we presented in the first lecture. So analysing the measurement process, identify the influence quantities. We know how to do that now. That's really from lectures 1 and 2, just recognising what the error terms are and how they influence the measurement. List any simplifying assumptions and their impact on the measurement. Form a mathematical model of the measurement in terms of the influence quantities. So you know how to do that now, and hopefully that would be expressed in some optimal form. Step 4, evaluate the sensitivity coefficients of the influence quantities. Step 5, evaluate the standard uncertainties and the degrees of freedom. Step 6, determine whether you've got correlated components or not. And step 7 would be to calculate the combined and expanded uncertainties and the degrees of freedom for the overall process, and then round appropriately, of course. Okay, so we've pretty much come to an end. There's a lot of material there, I appreciate that, and there's quite a bit of mathematics, which can be quite complicated. It's not the easiest subject to teach, and by far the easiest method, if we weren't doing this remotely, would be to sit down in class and go over an uncertainty budget with you. So definitely the way to do this is to do an example. So you can literally pick up a ruler, you can take repeat measurements of an object, and you can think about how you would calculate the uncertainty in those measurements and go through this process, set up that table with all the influence quantities, and go for, just going through this process allows you to learn the process. And I think pretty much at the level you need to be at for this course, you can ignore the correlation terms. There is this is purely out of interest, that what we've been talking about, all the statistical methods we've been using have been what's called frequentist statistics. There is another approach to statistics which is called Bayesian, and so the method that's in the GUM is frequentist, but people are seriously considering going towards a Bayesian approach. So at the moment, GUM is based on frequentist, and there are a few elements of Bayesian. So what's the difference between the two? So the frequentist method is basically where it's saying that the uncertainty is due to randomness, whereas Bayesian is saying it's due to a lack of knowledge. It's a subtle difference. So in frequentist, we say the probability is equal to the frequency of events, and in Bayesian, we say it's the degree of belief or the state of knowledge. So we tend to, with Bayesian approaches, we tend to bring in all of the a priori information that we might have about a measurement scenario or an uncertainty calculation, and use that as well. So here's an example of frequentist view would say that 30% of the days in the year are expected to have rain. We would call that a long run average. So, but in Bayesian approach, you would say a given day has a 36% chance of rain. So it's again lack of information about a day. So this is an interesting philosophical differences, and there's a lot of debate about this in the uncertainty community. But there is some move towards a Bayesian approach. One thing about a Bayesian approach is it removes some of the mathematical difficulties about adding distributions together and things like that. Those start to disappear, and you can have a more harmonious approach which is based on rigorous mathematics. But that would all come in the future. So what have you learnt? Well, we've gone through how to deal with the various systematic and random errors that you get. We looked at the statistics, uncertainty distributions. We've now done confidence intervals, the standard uncertainty concept, how to propagate uncertainties, how to do that with multiple variables, and how to express that final result. Okay, thank you very much.